In this lecture, let us look at some of the design basics of subsonic wind tunnels. We have picked out the closed circuit low speed wind tunnel for this discussion. So, we are showing that general layout of such a tunnel here with all the major features in place. So, we will go around the tunnel circuit and we will look at each and every component to understand how those components function and how they get integrated to ensure the functioning of the tunnel. So, how do we start going around the circuit? We start with the test section and then we will go downstream by following the path of the air, and we will move from one component to the other looking at their features. So, we begin with the test section and that is located here. Here it is shown as a closed test section, but it can be an open one. That means, you can have an open jet facility, or you could be having a tunnel where you can function both as a closed one or an open one. That means, you have a convertible test section, but in such cases usually it will be more meaningful to build an enclosure around the test section. And then you should also have suitable facilities to prepare for the change of the test section if you have multiple test sections which you may be using for different kinds of experiments that you would like to perform. Therefore, this enclosure could have all those facilities. Additionally, the enclosure could also house the data acquisition systems, the measurement instrumentation, the model positioning system. The staff could be located over here who are taking care of performance of the different tests, etc. So, this room has multiple utilities. It is not explicitly shown as a part of the sketch, but nevertheless it is very important to have one. Additionally, in open jet facilities, if you do not have an enclosure around the test section, there is often a problem that instead of the air coming in from the settling chamber part and the contraction section part, a large part of the air gets dragged from the ambient into the jet and then continues into the diffuser. Therefore, the jet gets extremely disturbed. Therefore, having an enclosure, a room, an airtight room is always a better idea in that case too. The test section length to hydraulic diameter, which becomes important if you have a non-circular test section, ratio is 2 or more. That essentially defines the length to diameter ratio of typical test sections. After you cross the test section, you move into the diffuser region, which is just downstream of the test section. And by thumb rule, the length is 3 or 4 times the test section length. It is just a thumb rule. And then if you imagine that there is a kind of cone which is emerging from here, because it is a divergence that you are looking at, the typical cone angles are in this range 2 to 3.5 degrees, which is a very shallow increase. And the smaller angle is more desirable, or the smaller angle range is more desirable. Why is it? Because this ensures that the adverse pressure gradient which builds up in the diffuser, because the flow is slowing down and the static pressure is growing. So, it becomes more challenging for the boundary layer part of the flow to remain attached. So, here you need to keep the adverse pressure gradient low, at least not too large, which can induce flow separation. So, you have to be very, very careful about preventing flow separation. If that happens, then the tunnel becomes very inefficient in terms of energy consumption. Moreover, the flow gets extremely disturbed in this region, and then it is very difficult to come back to a good quality flow by the time it returns to the test section. That means, if there is a separated flow here, there will be some trace of flow disturbances when the flow returns back to the test section after completing the circuit. The area ratio between inlet and exit of the diffuser, it is typically 2 to 3, with smaller values preferred. And remember that you are doing it over a fairly long section, and therefore, gradually the area is increasing, so that the dP dx is small, if you call this as the x direction. After it reaches the end of the diffuser, there is a corner. So, that is the first corner, and that has turning vanes for smooth turning of the flow. So, these lines which you can see over here, these are turning vanes. They are more like airfoil sections. Okay. So, when you are looking at the flow approaching the end of the diffuser and then going into the turning vanes will be shaped like this. So, they reach out to the flow and make the flow turn smoothly, again ensuring that there is not too high a camber which can induce flow separation. So, that you have a smooth turning, and then again remember that there is a cascade of blades. There are adjoining blades which route the flow smoothly through that cascade of blades. And then once it turns, it takes up this direction, it moves on. You have the second leg of the tunnel. This is the second leg of the tunnel. So, this is the first corner followed by the second leg, and the second leg could be a constant area section, in which case the flow does not accelerate or decelerate, but it could also continue to have the diffuser action, in which case there is a gradual increase in area even in that section, and the flow slows down further. Then comes a safety screen somewhere here, and it is used to prevent parts of failed models or failed or loose wind tunnel components, measurement instruments, etc., which have fallen and are being carried by the air. They cannot reach the fan, they get trapped in this safety screen. So, this screen is extremely important to ensure that things do not fly around through the tunnel circuit, but get arrested. Most importantly, get arrested before they reach the fan, otherwise it would damage the fan entirely, because they are all moving at high velocities. This screen usually is placed just ahead of the second corner turning vane. So, these are the second corner turning vanes. Again the flow takes a turn just like it did at the first corner, and then it is heading towards the fan. Now, the fan is mounted using supports on the inner part of the wind tunnel section in that region. So, there are supports on which the fan is mounted, and remember that the fan is being run by a motor. So, there is a casing around the motor which you can call as a fairing. So, it gives a nice aerodynamic shape for the flow to move externally past it, and then the motor is kind of shrouded inside that. The cables make their way through those supports to the motor. They are also housed within those fairings, and then Downstream of the fan, there are also flow straighteners. Now, before all that happens, the tunnel in most of these sections, the test section, the diffuser, the corners, the second leg, etc., these often have square or rectangular sections, but the fan section obviously is circular. Because the blades are sweeping a circular locus. Therefore, there must be a transition from the square or rectangular section to the circular section. So, after the second corner comes a transition. Before we move on to that, let us have a little more discussion about the second corner. So, the second corner turning vanes are often copies of the first corner vanes for ease of manufacturing and construction cost reduction. So, it has engineering advantages if they are replicated with the first corner vanes. We were talking about transition from rectangular or square to circular cross section to take the flow into the fan section. So, that comes somewhere here. That is the transition region. And then comes the fan motor assembly and flow straightener section. The flow straightener section comes just after the fan. And what does it do? It minimizes the swirl at fan outlet. So, when the fan blades rotate, they induce a lot of swirl into the flow. Flow straighteners negate that effect and make the flow more or less axial again. Then comes the return or second diffuser, that is this region. This is the second major diffuser. The first major diffuser was this, which was coming immediately downstream of the test section. What does this second diffuser do? First of all, it incorporates transition back to rectangular from circular cross section at the fan. And then the transition begins in the flow straightener section and then continues in the initial part of the second diffuser. Additionally, the second diffuser also has to increase the flow area gradually, keeping in mind that the pressure gradient cannot become too adverse. So, similar guidelines are followed as were discussed for the first diffuser. Remember that having the rectangle or square cross sections are useful for handling the tunnel for the engineers and technicians which are maintaining the tunnel. They are also easy to build and they are cheaper to build, and therefore, most sections of the tunnel and the test section are built that way. However, it has to be circular in the fan motor assembly region. Then we come to the third corner. That also incorporates turning vanes, but as you can understand that these vanes are usually larger in number and could also be larger in size. Again, there is a scope for their replication in these two corners, the third and the fourth corner. And the third leg of the tunnel lies between the third corner and the fourth corner. Again, the third leg can have a constant area most often. We were discussing about the air of the tunnel getting heated up for long periods of operation, in which case you would need to have a heat exchanger. Also, you need refrigeration for special tunnels, for example, icing tunnels. or if you are using it as a propulsion tunnel where you have to create temperatures corresponding to high altitudes. So, there could be different reasons for having a heat exchanger, which could be placed somewhere here. We have already discussed about the fourth corner. The fourth corner also includes turning vanes, and they may be copies of the third corner vanes like we discussed, because it has a cost and manufacturing advantage. Then comes a very important section which is called as the settling chamber. We have come across it even in the context of an open circuit tunnel. So, you remember that the open circuit tunnel had began with that flow getting into the settling chamber through the inlet, and it was looking more like this. Remember that this is what I am drawing is more like a elevation view, while what you see over here is more like a plan view. So, if you were looking at the closed circuit tunnel even in elevation view, then you would have seen something similar to this. Only difference would be that it would continue over here because it is a closed circuit with the remaining components coming. Usually it will be longer. And once it takes a turn, you cannot show it in the elevation view, but you can do it in the plan view, and therefore, the plan view is more convenient to discuss. Going back to the open circuit one, we often call this as a bell mouth, which ensures smooth flow of air from the surrounding into the settling chamber. Here, of course, in the case of closed circuit tunnel, there is no question of a bell mouth. The flow is coming from the fourth corner, turning and then making its way into the settling chamber. And then inside the settling chamber, you have flow conditioners, typically flow straighteners, turbulence control screens, which are shown using different lines over here. So, there are screens of different sizes which are arranged starting from larger to finer sizes one after the other, which will reduce the turbulence significantly. And then we come to the contraction section or the nozzle, where the flow accelerates and gets into the test section, which happens to be the lowest cross section part of the tunnel. Therefore, highest velocities are available here. Not only that, as the flow moves through the contraction section, it also gets quieter, the turbulence reduces further. Usually, higher order polynomials are often used for defining the contour of these contraction sections, and typical area ratios across a contraction section would be between say 7 to 12. These are ballpark numbers which are coming from widely practiced design principles. As we said earlier, the plane of the return passage is almost always horizontal. That means, the return passage, though we see it is above the passage which is containing the test section portion, but remember that it is in plan view and it is not to be interpreted as an elevation view. Therefore, it is actually horizontal. Only very rarely do we make the return circuit vertical, but that too when space is at a premium and for smaller facilities. In most facilities where these constraints are not there, the whole setup is made horizontally oriented. It saves cost and also makes the return passage easier to access for the engineers and technicians who maintain the tunnel. So, we got some idea about how things are working here. Let us discuss about some ways of assessing how efficiently a tunnel may be operating, for which we introduce a few concepts here. First, let us look at how much power is contained in that high velocity jet through the test section. Now, the power of the flowing air jet in the wind tunnel test section, that can be indicated as PT, T for test section. And how do we evaluate it? It is half m dot T into V T square. So, it is like saying half m V square, which is basically the kinetic energy content, and then you are taking a time rate of that. That gives you the power. And then m dot is rho times A times V. At the test section, it is all T subscript. Remember, we are talking about low speed tunnels, and therefore, in general rho can be considered to be constant because of obvious reasons, but still we are demarcating it with T here. And then if you use this expression, you can very easily show that the PT can be expressed like this. You see that PT is proportional to Vt cube. That means, the power which is contained in the air jet, it varies as the cube of the velocity, and therefore, as the velocity of the test section rises, the power involved is also going to be huge. Additionally, for larger sections, you will be talking in general about larger mass flow rates, and also power consumption will go up. If you were to look at the test section velocity in terms of say meters per second, if you take a velocity of the order of say 8.94 meters per second, you can calculate it yourself also. You will find that the jet power would turn out to be 0.44 kilowatt per meter square. So, if you use unit cross sectional area, then this is the power which will be contained in it. Now, if you say you increase the speed to about 22.35 meters per second, and then the power becomes many-fold more per meter square. It is happening because of the cubic variation with velocity. So, you can do similar calculations yourself and see for yourselves how the power contained in the jet increases gradually, or rather quite rapidly, as the velocity in the test section increases. So, that is the concept related to jet power. Let us look at the next concept, energy ratio. Now, the ratio of power in the test section flow to the rate of flow losses around the wind tunnel circuit is a measure of its energy efficiency. Why do these losses occur? It is by and large viscous losses, which are irreversible. There would be losses, you cannot do much about it, but you can keep the flow separation to a minimum, etc., so that the losses are minimized. Therefore, you have to manage the aerodynamic design of the tunnel well, so that the losses are kept to a minimum. That is the basic strategy. Now, how do you assess the energy efficiency of the tunnel? It is through this energy ratio. What is the definition? It is the ratio of power available in the jet flowing through the test section to the power consumed by the flow losses incurred in the wind tunnel circuit, which is quite obvious that this is the power you are getting in the jet, and this is the power that you are wasting through the losses, and therefore, the larger the scale here, the better it is in terms of energy efficiency. Now, these losses are not coming from a single point in the tunnel. There are so many different components which make up the tunnel. We saw it in the previous slides that there are so many components, so many elements through which the flow is moving. The flow is also moving at different velocities, because in a low speed flow, how does the area velocity relation work between two sections? This is how the area velocity relation will work. So, as area increases, the velocity reduces, or vice versa. Now, let us say if you were to apply the Bernoulli's principle, which we learned earlier. So, if we were summing up the static pressure and the dynamic pressure and we were applying it across two different points. So, if this is an upstream point and you select another downstream point, they will never equate because there are losses involved. In general, this would have a larger content of the stagnation or total pressure compared to the downstream location. However, the dynamic part just follows the continuity equation and works out. So, it may be that the static pressure would vary from what is defined by Bernoulli's equation and will be lower than what Bernoulli's equation predicts, while the dynamic part has to be kind of maintained because of the continuity equation constraint. So, think over it that in a viscous flow, the stagnation pressure reduces, that is also an indication that there are flow losses, and whether that also indicates that static pressure also reduces as the flow moves through the circuit. So, there must be a mechanism by which you try to sustain that static pressure by increasing it at some location, and that is precisely what the fan does. So, as the pressure drops off, the fan increases it abruptly and then allows the flow to again move on with an enhanced pressure, so that it can make its way through the circuit and overcome the losses. Now, if you move along the tunnel from one component to the other, you can define a section loss coefficient. What is the idea? At a certain location, if you pick up a certain component, then the total pressure or stagnation pressure drop in that local section or the local component, which we are demarcating as L, if you take a ratio of that with the dynamic pressure at the entrance of that section L, then that gives us a section loss coefficient, which we define as KL, L for local. So, this is the total or stagnation pressure drop across that section, and this is the dynamic pressure available at the entrance of the section. Let us say if this was the first diffuser, then you are quantifying what is the loss in stagnation pressure across the diffuser, and you are also quantifying the dynamic pressure at its inlet, and you are essentially taking a ratio. You are indicating the dynamic pressure by QL. What is the time rate of energy loss in this section? It is the product of total pressure loss, which is this, times the volumetric flow rate. That gives you the time rate of energy loss. This is your flow rate, you multiply it with the stagnation pressure loss, and then what is your stagnation pressure loss? It is KL into QL. So, that is how you get it. You take the KL aside and the rest of the terms look like this, where you are showing the details of the QL term here, and then you write those terms in this manner, so that you can get the m dot expression from this collection. So, what are you left with? You are left with KL into half m dot VL square. Let us see how we can reorganize these terms a little further. We will define the section loss coefficient further, which we showed as KL earlier in the previous slide, as referred to the test section dynamic pressure, which we define as KL suffix T. What do we mean to do? We use the same stagnation pressure loss for the L component, but now divide it or scale it with QT, that means the dynamic pressure in the test section, which you can express as delta HL by QL into QL by QT, and that delta H by QL is nothing but KL. So, KLT, that means the delta HL scaled with QT is nothing but KL into QL by QT. Finally, remember that from this equation, what can you write? You can write KLT times QT is KL into QL, and delta EL has been shown to be equal to KL into QL already, and that happens to be also equal to KLT by QT by this equation, and further as KLT into PT. The total rate of loss in the circuit now is obtained by summing the rate of section losses for each of the individual sections. So, we take a sigma over all the local sections. So, that summation of KLT into PT. Now, PT is a fixed quantity. So, that comes out of the summation. So, what are you left with finally? The energy ratio, which by definition is PT by PC, is now visible from this equation as well. So, that happens to be 1 by the sigma KLT by clubbing this equation with the earlier definition of energy ratio. So, now we have an alternative representation of the energy ratio in terms of summation of all the sectional loss coefficients. Now, from this we can further take note of two very important points, that the energy ratio for closed circuit or open circuit tunnels, importantly both having closed test sections, they typically range between 3 to 7. That means, this ratio varies between 3 to 7, while the energy ratio for a free jet facility, that means it is an open test section, it is always less than 1. So, whereas this ratio is 3 to 7, this is less than 1. That means, there is a wide gap in energy ratio between the two categories, which obviously means that the free jet facilities are very less energy efficient. And this is precisely one of the important reasons why no large size facilities use the free jet configuration. So, we will conclude now. In this lecture, we discussed about various components of a typical low speed wind tunnel. We took a closed circuit tunnel, and additionally we introduced the concepts of jet power, energy ratio and section loss coefficients. Thank you.